Good afternoon, everyone. Thank you for joining us for this installment of the PENC webinar series. My name is Katie Cox, and I'm the PENC Membership Director. I will be serving as moderator for today's presentation. If you have any technical difficulties, please use the chat box and I will try to assist. Feel free to ask questions throughout the presentation by using the questions chat box. Today we have Aaron Earwood and Josh Taylor. Aaron is a professional engineer in North Carolina. He graduated from UNC Charlotte with a BS in civil engineering in 1998. He worked with the North Carolina Department of Transportation as a resident engineer in construction for 10 years, continued with NCDOT as an area bridge construction engineer for 8 years, and is currently the Eastern Regional Bridge Construction Engineer with NCDOT. Josh Taylor is a PE in North Carolina and Utah. He graduated from NC State with a BS in civil engineering in 2000. He is a senior bridge engineer with Parsons. Thank you so much, Josh and Aaron, for being here.
You're welcome. Glad to be here. I would like to thank you for inviting us to present on this topic today. This is Aaron Earwood. We originally developed this presentation for ACEC to transportation designers and construction community, but we're been asked to present this topic to PENC, and we're very happy to do that. So hopefully you'll get some good information out of it. As she said, I am a bridge construction engineer, whereas Josh is a structure designer. So in looking at this and putting this presentation together, we come from two different perspectives, and they both have a lot of overlap because what he designs, if he doesn't take constructability into consideration, will make my life much more difficult when we try to build it. So as we go through this presentation, we will be kind of tag teaming it, going back and forth between Josh and I, and hopefully things will flow well and get some good information out of this topic. As far as staged bridge construction, you know, when we're building bridges, if we can build them, you know, traditional methods, obviously that's the preference. But with today's traffic volumes and tight right-of-way and utilities, it's very rare that we get to just go out there and build a bridge with normal conventional methods. We're faced with having to stage the construction just because of the things we're faced with. So as we go through this, we're going to hopefully define what stage construction is. You know, what is it? Why do we do it? And then we're going to get into some different perspectives as far as the superstructure, how that's impacted. Getting into our substructure and foundations, how we handle that, and then finishing up with a little bit of talk about stage approach build. So again, like I said, we're going to kind of go back and forth on this presentation.
Great, thank you, Aaron. Okay, so let's define stage construction first. The full width of the bridge will be constructed in stages or phases. You know, there will be a portion of it that has traffic on it while the other portion is being built. And then ultimately these two, you know, come together to form the whole and the finished product. The stage construction gets utilized in basically three different conditions. The most predominant conditions are when you're replacing a bridge that's already in service, when you're widening a bridge that's in service, and then occasionally you've got a special condition where it's beneficial to do stage construction in a new location. And Aaron will touch on that a little bit more for kind of a special topic for that, in addition to just right-of-way and easement and utility concerns that can also get in the way. All right, so why you would want to use stage construction when you're looking at a bridge replacement? You know, you've already got active traffic, you know, in the area where you're needing to do the bridge replacement, and so it may not be practical or feasible to, you know, just take people completely off of the bridge that's there, to temporarily or permanently realign the roadway, or just do a total off-site detour. You know, there's impacts with that. You know, you got to consider maybe having to buy some right-of-way, environmental problems, increase in cost from temporary bridges and approach roadway that comes into it. And some roads, you just can't shut them down. They're too busy. The traffic volumes are too high. There's just no way you could effectively, maintain, reasonable traffic conditions and shut down that road. For example, interstates, bridges, roads that are on the national highway system, regional tier classification routes. And then sometimes, there'll be maybe just even a smaller structure that needs to be replaced. You have to do something in a stage constructed way because you don't want to just completely cut people off. You can't do that. You can impact access to schools and hospitals and or give somebody an unreasonably long detour. So these are things that are very important, I think, to the DOT, and we always take that into consideration early in the planning process for deciding how bridges are going to be replaced. When you're looking at widenings are great in that you're most often able to maintain traffic on the bridge while you remove a small portion of it and then continue to build onto it. So you can typically avoid any kind of detour conditions with a widening. So those bridge replacements and bridge widenings, those would be reasons for using stage construction.
So another case that I wanted to talk about briefly would not fit into those criteria that Josh just covered, where we're trying to either detour or maintain traffic on site. This could potentially be on a new location, say like a Raleigh or Charlotte outer loop, where we don't even have any traffic. But when we have very wide structures, and by very wide I would define that as anything over 120 feet along the skew of the bridge, that can create problems. And the 120-foot dimension is derived from that is the maximum width that a typical bidwell screed can span without significant truss modifications. So once we get over 120 foot, we need to be looking at other alternatives. And that could be stage construction, where we basically build half, and then we build the other side, and then we close the middle with the closure pour. So that's one option. But I have had a couple bridges where the contractor has actually utilized two screeds with a screed rail down the middle. So they've got their typical screed rails on the outside, and then they put a third screed rail down the middle, and you can see the two trusses, the screeds that are staggered slightly, and they basically poured the bridge using those two screeds at the same time. They utilized two separate pumps. So it was almost like two separate concrete pours going on at once. And by doing this, they did not have to stage construct. So that was a good innovative way to expedite the project and to avoid having the stage construction. The first time that I dealt with this, the contractor just proposed it. The second time I knew it to be done, and so during design, we decided to not show a closure pour on the plans and stage construction, but give the option of the contractor to do it. That way they had the option to do it in the two stages or do something similar to what this contractor did. So this was a very successful pour. I think they poured about 750 cubic yards of concrete in that one pour. So it was pretty innovative and worked well to avoid stage construction.
Okay, so now with that groundwork on what it is and why we would do it, let's take a look at some of the details of the implementation as far as the superstructure is concerned. I'm going to switch my mouse mode here to show a laser pointer. Okay, so we're going to be defining a closure pour on this slide, and here in the upper left-hand corner is an existing two-lane bridge, and on the bottom shows the full width of the future structure, the one that we're going to be constructing. So we're going from 2 lanes to about 5. So obviously there's a lot of traffic here to justify that large of a structure, and that explains, in part why we would need to do stage construction here. So you start out by building one half of the bridge, designated stage 1 while traffic is maintained on the existing structure. Once this was completed and has a portable concrete barrier rail erected here to make that a safe edge for both the public and for the people who are working on the other side of it, you move your traffic over into that portion of the bridge. Then you come and you build the remainder of the new structure. And then what we're really honing in on here in this presentation is what are we doing when it comes time to connect those two with the stage 3 deck closure pour right in this area. So that is where you build one half, move traffic to it, build the other half, then connect the two, and then you're ready to open the bridge to final service. So that's kind of the definition of a closure pour, this little closure area that connects the two structures that have been constructed partially. Then we have an alternative condition. Get out of this pointer mode. This is a real creative name here. This is called a non-closure pour. And it's an alternative to using a closure pour. It's applicable under some more constrained conditions, which we'll discuss. But usually that means you have a narrower structure with spans that aren't quite as long that permit this type of construction, where you would come and you would add directly onto an existing bridge or an existing portion of a newly constructed bridge in order to span it out the rest of the way. This will, there's criteria that allow you to use this condition. It's an alternative that's open to you, but the closure pour, you're always welcome to use it. Sometimes a set of plans will have a closure pour details, and the contractor will come back and say, I think I could do this with a non-closure pour approach, and it would be beneficial, for them. So, we'll review that and make any modifications that are needed to facilitate that. In a case like this where you're using this on a widening, which is, kind of a typical condition where this would occur, is what we're showing in this diagram. You would often use a latex modified concrete overlay to help improve the rideability as you go, from across this joint that gets created. I've got a note here, for the design engineers, that when you're scoping this project, you would want to consult with the area construction engineer, i.e. Aaron here, to see if this approach would be considered beneficial. If not, you would default to using a closure pour. Okay, so a couple more minutes for me here. The method of making a selection on the closure pour or the non-closure pour. The non-closure pour is limited, and you cannot use it on steel structures at all, just due to their inherent increased flexibility. And then with pre-stressed concrete girder superstructures, there's some limitations on the span length. All spans in the bridge have to be less than 85 feet, and all spans have a non-composite deflection limit of 1/2 inch. If you meet those criteria, then this is a candidate approach that you would want to consult with the area construction engineer to see if they feel that would be beneficial for this particular bridge design. Otherwise, you use a closure pour. And so the question is, well, what's the difference between those two? What are some driving concerns behind the deflection and the span limits? And it has to do with both deflections and the time that it takes in order to get concrete cast. This diagram is showing the incremental increase in dead load deflection as the concrete pour progresses from back station bearing to the head station bearing on a presumed simple span structure here. And just to talk some of the numbers a little bit, when you've got 1/4 of the span placed at the quarter point of that span, you will see 17% of the deflection that will ultimately occur when the span is completely poured. And so following that quarter point through, when the span's halfway poured, you get to 54%. 3/4 poured, you're at 87%. And when you're finally done with the pour is when every point in the bridge has reached its final deflection amount that it's going to be experiencing under the dead load application. And so the timing of this is an important consideration, and you can also run into a condition that is known as wedging, and I'll let Aaron talk to that one.
Put it back on that last slide. Okay, leave it real quick. So the reason this is important when we're constructing bridges with this deflection as we pour and the pour progresses. On a typical bridge, for those that are not familiar with bridge construction, you saw the bridge screed, how you ride on a screed rail, and typically that's placed on an overhang outside of the exterior girders. And as concrete is placed and the girders deflect, the screed deflects with it the same amount because they're both deflecting. So as you pour and place concrete and screed that deck, you maintain your deck thickness, and as your screed advances and the girders deflect, it continues to follow those girders. So you always maintain your deck thickness. The problem with stage construction is let me back up. If you do stage construction and have a closure pour, you do stage 1 and then you do stage 2. They're both independent. So you pour those with conventional methods. Your screed goes down as your girders deflect, and that's no problem. And hopefully your left and right side deflect the same, and then you come in and pour your closure pour. On the non-closure pour, the problem this creates is on the outside, my screed rail is being supported by a girder that is not yet deflected and that will deflect during the pour. But on the left side or the other side, my screed rail would be running on the deck beside it that is already deflected, and it's not going to deflect anymore. And so as I pour, I have one side deflecting and the other side not. But all my girders on the widening are deflecting. And so if I place concrete and then start screeding that deck, I'm in essence cutting a wedge off my final thickness. So I will have less than my planned thickness on my deck, closer to that phase line. And that can cause a problem because I'm not going to have my cover over my reinforcing steel. And then as it continues to deflect throughout the pour, it could potentially cause low spots as well. So that's why when Josh talked about the 85-foot maximum concrete girder limitation and the half-inch maximum deflection, that's why we have those limitations so that we're not getting much deflection. So if it does impact us, it's very minimal. If we had 3 or 4 inches of deflection on a span and we tried to do that without a closure pour, we would be having some serious problems. So that's kind of a brief explanation of why it matters without doing the closure pour. If you are in that range of a half inch, or if the contractor proposed to eliminate a closure pour and it slightly exceeded what was in the design manual and it was agreed upon to allow it, a couple things that you could do is preload the span to try to go ahead and get some of that deflection out before we screed it. Typically, we like to keep the leading edge of the concrete about 5 to 10 feet ahead of our screed. But in this case, preloading it out onto the span, maybe halfway the span, maybe 3/4, gets most of that deflection out before you start screeding. Now, there's obviously a risk because you got a whole lot of concrete out there that if the screed breaks down or something happens or you get rain, you're left out there with a whole bunch of concrete that hasn't been finished and could be very costly to deal with from a contractor's perspective. But under certain circumstances, if agreed upon by the engineer with the DOT, we have done this. And one thing I like to do if I was going to preload would be to keep the concrete below the top mat of reinforcing steel. There's 2 mats on our decks. And then they can kind of preload and then come back and then place fresh concrete in front of the screed, vibrate the 2 to make sure we don't have any cold joints, and then continue to go back and forth and advance the screed. And that would mitigate some of those effects that I described. Another concern with eliminating the closure pour, if you have larger deflections or don't preload, would be you're placing concrete around your reinforcing steel, you're screeding to that phase line, and then as it continues to deflect on your stage that you're pouring, your reinforcing steel and dowels coming out of stage 1 are not deflecting, and so it could potentially leave some voids around those bars and reduce your bond, possibly lead to reflective cracking. So those are some other considerations when dealing with this without doing a closure pour. That's why we evaluate it so much, to make sure that when we are not doing a closure pour, that it meets certain criteria and we're comfortable with it. So here's just a good picture of what a closure pour is. Again, left side and right side stages have been completed. Closure pour is basically what it sounds like. It's closing that gap. They can range in width, and we'll talk about it a little bit more, but typically it's small enough to where the contractor is just going to use some form of a straight edge to finish that concrete. If it gets too small of a closure pour, you can have issues with your left or right side possibly not matching up as good, and it being a more severe slope between. If it gets too far, your finish in between the two might not be as good. So considerations to think about whenever we're deciding how wide that closure pour is going to be. This is a diagram of a pour sequence. So when we pour our decks, typically we use the Wisconsin pour sequence, and I'm not going to go into that in detail. But there's a specified pour sequence depending on where the vents are and the spans. And so we specify where the transverse construction joints need to be, and we number the pours in a certain order. And there's a whole another topic and discussion on that. But the point I want to make is whenever you need to design the stage of your construction based on that pour sequence, but when you come to pour the closure pour, because your deflection has already happened in your deck, if there's any deflection at all, it's very minimal when you're pouring the closure pour, and so that does not have to be divided up with transverse construction joints. I've seen plans that have shown that, where the closure pours are divided up to match those transverse joints, but that is not required because of the lack of deflection. I'm going to get a little bit into deck forming, particularly in the closure pour region. And if there's one thing I learned or picked up on and put in this presentation together, was that there's lots of different ways to do this. Different contractors or engineering firms have different preferences, and based on the situation, have different alternatives. And so there's no one-size-fits-all method. And so I'll just kind of go through a few of these. You can see in this picture, we've kind of highlighted it in yellow because it's hard to see because of the shadows, but that girder is, it looks like they've already poured stage 1 on the left of the screen. They look like they're getting ready to pour stage 2 deck. So they've got their overhangs, and that's an overhang bracket that they've placed. And so they'll run the screed rail right on that overhang, and that side will deflect independently of stage 1. So that's how they're supporting their screed rail and supporting their overhang on this particular case. So this picture on the right is completed stage 1. On the left, you can see the girders and the metal decking. That stage 2 has yet to be poured. So what they have done is they have basically floored in where the closure pour will be, but they're using that for their screed rail as well. So whenever they pour stage 2, they can wreck that side form and then pour the closure pour. The important thing, and I mentioned it before, is whenever you pour that second stage or you're widening, it has to act completely independent of stage 1. We don't want anything tied together such that it would limit the deflection when they go to pour that stage 2. We want it to deflect like it was designed to. And so the next slide you can see here is underneath, and they've got overhang jacks and decking, and then you can kind of see the coil rod hanger that they hung from stage 1, supporting that deck forming. But it can kind of pivot and rotate, and it's not going to limit the deflection when they pour that next deck. Here's another diagram or drawing where they did not use overhang jacks. So on the left side is stage 1, and you can see they've got a coil rod and hanger coming off of the reinforcing steel from stage 1. And then on the right, when they're doing stage 2, they've got that 90-degree half hanger supporting the false work to be able to floor in that closure pour. And so as they pour stage 2, again, it can kind of rotate and pivot and deflect. And then once they finish that, they can pour their closure pour. This particular contractor chose to use all overhang jacks, and so they, although it's hard to really see what's going on, they poured stage 1, used the overhang jacks to support their false work, and then they set the girders on stage 2, put new overhang jacks on that side, kind of overlapped them, and then floored in over top of them. So they were able to act independently of each other, but that's their methodology of what they chose to do in this case. The final one topic or way that I've seen contractors do this, and this is something that we used to not allow, and the reason is, so you can see the metal decking, the silver stay-in-place forms. Typically, that's how we form our decking, our false work is metal stay-in-place forms, unless you're on the coast, and then we use pre-stressed deck panels. But up until several years ago, our closure pour longitudinal joints by policy had to be off the top of the girder. We had to make them offset from the girder a certain distance. We started allowing that longitudinal construction joint to be placed right over top of the girder, again, several years ago. And what that opened up the opportunity to do was go ahead and place your metal decking in your closure pour bay, as we always do on typical bridge construction. And so it's just a faster, easier method, and it can span wider widths, possibly even allowing a designer to not tighten your girder spacing in that closure pour bay, because typically we have a tighter girder spacing in that closure. But by this method, they could potentially have 8, 9, 10 foot even bay in the closure pour and use the metal decking as their false work. So one consideration, if you choose to do that as the designer, you can see on the left, it's highlighted, that's our typical stirrup design coming out of an ash toe girder. On the right block, you can see we have to put a screed rail right down the middle with a side form, and so having that connected S2 bar would not work, or would make it extremely difficult. So as a designer, you'd have to recognize that if you're calling for that construction joint to be over top of the girder, you have to modify the stirrups coming out of the top of the girder, which is standard and it's not a problem. Just you have to recognize that so they don't cast the girder with the connected stirrup. I'm going to let Josh talk a little bit about longitudinal joint placements.
So for longitudinal joints, there's some best practices that are in play, recommendations that we observe depending on the structure type. For pre-stressed girders, you will typically locate your longitudinal joint just off of the edge of the flange. We're discussing here a way that you can put it right down the middle, and that's acceptable too. But usually you want to have it at least 3 inches offset from the edge of the flange in order to accommodate, room for the hardware that the contractor will utilize in order to create the forming that's needed. And for steel girders, they do not allow in North Carolina to place your joint right down the middle of the steel flange, so you need to do an offset, and again, about 3 inches off of the edge of the flange is recommended.
And just to point this out, currently by our design manual policy, it does not speak to that 3 inches. And so if you went strictly from the design manual, it would not do that. But that's what we're recommending, and hopefully the design manual will be updated to recommend at least that 3 inch minimum.
See, I'm already there. I'm ready to do it. Okay, so some additional placement recommendations for longitudinal joints. You try to place them where they're not going to be getting beat by traffic. Put them in a shoulder if possible, below a median if possible. Additionally, you want to place them on a crown point, where bridge decks are super elevated for drainage purposes and for horizontally curved structures. The super elevation is also very important safety consideration for handling curves. But you want to either put your crown point, on that joint, or have your joint at least 4 feet away from the crown point, again, for good implementation of the screed operations in the field.
Yeah, and the reason that 4 feet is that we need 4 feet or more, when we're screeding a bridge, the screed can only come within a couple feet of the side form, where and from that point to the outside, you got somebody hand finishing that area. And so if hand finishers have tough enough time just projecting that 2 foot straight based on the super elevation. So if we asked somebody that was trying to hand finish a crown break and get that consistent, it would not go well. We would not get good results. So we want the screed to do the work and have a break in that crown point. And so we want to make sure we have at least 4 foot to allow the screed to come, make that point, and then the hand finisher can finish that other couple feet to the side form. So that's where that 4 feet came from.
Here's just a graphic showing what's considered to be the wheel path, where you try to avoid placing longitudinal joints when you're involved in your girder layout and figuring out how you're going to make everything all fit together in stage. You want to take the wheel placement into consideration. When it comes to non-closure pore joint locating, specifically when you're doing widenings, here's 2 diagrams to show a preferred way to do it and a way that's not preferred. You prefer in the upper diagram to get on the inside face of the barrier rail that you're going to cut off and make a vertical cut and go right down through the deck in order to make space to add in the new structure that you're going to be adding. An alternative to that that's not preferred is that you're coming down right on the center line of an existing girder or somewhere on the top flange. You want to try to avoid that so you don't end up damaging the stirrups or the girder itself, or studs, if you got studs going on. So in a case like this where we're showing an existing concrete barrier rail that's right on top of the girder, it's kind of ugly to deal with in the field, I think, but you can also do a horizontal saw cut in that location to avoid going down into the girder. So here they kind of had no choice, other than to horizontally cut it. So about longitudinal joints, they are not perfect, and so that's partly why there's so many considerations as to where they can go and what's ideal. Is because they'll leak. If the openings at this joint are greater than 0.007 inches, they're not going to function as though they're sealed against water or chloride penetrations. And the way you can tell that you've got a problem going on is you can get down below the bridge and take a look up and see if you've got any kind of formation of material that's leaking through the bottom of that joint. Sometimes you'll see rust stains even when you're using epoxy-coated reinforcement because it will rust over time. This diagram or this picture right here is from a bridge that had some real issues in Virginia. It's a bridge on I-81, and they were getting openings on the order of 0.008 to 0.015 inches, and over time that little bit of leakage in there compromised the steel that this whole section of the deck just fell through, and the rebar completely sheared off. So Virginia Transportation Research Council made some recommendations to, move your longitudinal joints over the tops of the girders, to use corrosion-resistant steel, or to use an expansive concrete in the closure pour to try and keep those interfaces sealed, where they'll tend to creep apart from one another due to differential shrinkage between cast concrete cast at different times. ACI 345 furthers with some recommendations that you could take and cut along the top surface of the joint when it's completed, and inject it with some epoxy and do some surface epoxy coating right there. When we were given this presentation to North Carolina DOT consultant and private bridge designers, so just pointing out these are not necessarily all in agreement with NCDOT policy at this point, so you want to adhere to NCDOT policy. Moving on to the girder spacing, inside the Department of Structural Design manual, they have some recommended spacing as a function of the girder type. And if you conform with these spacing limitations for a closure pour, then that has some cost savings later on down the line in terms of some diaphragm operations that have to accompany it. But it's also a flexible element, and if you can, when you're involved in the layout of the structure and you're considering using the closure pour, you can take a look at using a wider space if it will end up saving you a girder line, because that also provides some good, economic benefit as well. The department recommends using a 4 or 5 foot spacing when you're doing a widening as well.
And as a department, we are looking at evaluating these widths and working with our Associated General Contractor Committee to see about possibly modifying these recommended widths, particularly on the modified bold T girders, because it is very tight in between them because they have such a large top flange. So hopefully we'll have some updates on that soon. Here's a couple diagrams to just illustrate the type of ways that you form the steel inside of this connected area. Typically use dowels that are inserted into the header on either side, and so you have projecting dowels where you've already poured, and you lap them up with dowels coming from the other side. There are some alternatives to this, but this is what's typically done in North Carolina. So the design manual allows when you have 2 foot or less closure pour to only have 1 mat of steel in the top. So there's 2 things I want to speak on. The 2 foot closure pour, although it's allowed, and I think I mentioned it before, if your stage 1 and stage 2 don't deflect exactly the same, even if it's a 1/4 inch off or a 1/2 inch off, over a 2 foot closure, that can be a pretty extreme change in super elevation just in that to try to match, or it can take some extensive corrective action on one of the other stages to try to get a better tie. And most of these closure pours, or a lot of them, will be in the final traffic pattern. You'll have vehicles traveling over them, even though we make efforts to try to keep them out of the travel lanes or and put them in the shoulder, but a lot of them are in the travel lane. So the better we can make that transition is obviously preferred. So in my experience, the 2 foot closure pour does not give you as much opportunity to kind of have a less severe difference between left and right stages, or stage 1 and stage 2. And additionally, my preference, and I felt like this before I even saw the picture of the bridge in Virginia, but I feel like having the 2 layers of steel is just an extra layer of safety factor. So I always recommend to have 2 layers, and if we can, increase that closure pour.
Okay, so here's what we're looking at. Leave it untied until you're ready to make the pour. So
again, this picture here you can see, they've epoxied in their dowels into the stage line. This is a widening project because you can see the bars that were cut. The thing I want to point out with this is in demolition, typically when we're widening, we'll have a saw cut all the way through like this. But even when we're doing that, sometimes we'll get spalling on the bottom side of the deck. So the contractor needs to use good means and methods for removing that deck. Saw cutting, we have to deal with what's out there. So if the deck's in bad shape underneath, then we'll have to chip it out and patch that back. Sometimes a contractor will ask, instead of saw cutting all the way through, to saw cut just the top couple inches and then try to chip out the rest of it and maintain the existing reinforcing steel to splice on for the widening. And we have done that before, but part of the problem is with doing the chipping out of the concrete instead of saw cutting it, we get a lot more spalls like this on the bottom. And so that's a consideration the department would have to take in approving that or not. But typically we prefer to saw cut all the way through and then drill and epoxy in new dowel bars.
I'm going to touch briefly on the topic of live load vibrations. On the upper left-hand side, you've got a stage 2 that is subject to dead load only, while on the right side, you've got stage 1 bridge that's already up and running and holding traffic. And so you're coming here to do your closure pour. And so as the traffic moves along on stage 1, it's going to have instantaneous deflections as the traffic moves through. While on the other side, the deck is being cast and it's deflecting, and eventually it'll set into its final deflected position under dead load. But you've got this movement that's occurring on the right side, and so that can create some issues with bond and connection, the quality of the connection in the closure pour, and so some quick recommendations on this. There was a study that was done by FHWA that took a look at the magnitudes of deflections that would be typically encountered during stage construction. And so they took a look at 0.005 inches, 0.01 inches, 0.05 inches of deflection. They looked at different types of concrete, including those typical of what's used here in North Carolina, Class AA concrete for deck construction. And the basic observation was that the bond is reduced when the rebar moves on the order of a 1/16 of an inch. Up to significant bond reduction can be seen when you've got a 0.05 inch deflection. But down at the 0.01 inch deflection range, basically no observable effect. It was also noted that the frequency of the deflections don't really have an effect on the bond. It's just the magnitude. So some recommendations that can be brought into the design side of things to help improve this condition is to just try and get the you get the bridge smoothed out. Sometimes there's an opportunity to do some corrective action on the front end of a project in order to smooth the structure approach so that it's not a big hit when the vehicle comes on and you got this bouncing effect that's going on just because the bridge itself is in bad shape. I believe Aaron, you mentioned that you guys did something like that for a project in Division 6.
Yeah, so again, having a smooth approach onto the bridge where traffic's running, the smoother the ride is, the less impacts there's going to be. So a lot of times during the life of a project, we may not have the final lift of asphalt approaching the bridge. And so if you just have a short little kind of a wedge to get up onto the bridge, then that's going to create that bouncing action. So one consideration would be, and we did this in Division 6, which is the Fayetteville area, was to come back about 50 feet off the bridge and pave the final surface of asphalt so that any bouncing action is hopefully minimized once they're on the bridge. And that can be either milled out and replaced later, or potentially just used as the final surface. But anything you can do to minimize that bouncing coming onto the bridge.
Another thing you can do is temporarily, at least during the pour, and then in a short period after the pour is completed, you can close the lane that's immediately adjacent to the pour, just push everybody over so that maybe down to one lane if necessary, at least during that one phase of the operation. It can also reduce the speed so that, you know, people are just slowed down. They're not going to cause as much bouncing in the structure. And, you know, if you can use interchange ramps to divert people away, you know, right there during that critical time. But, you know, the general rule of thumb is that you want to get, you want to get your closure pours placed and then try to leave that area largely undisturbed for about a week. That gives the concrete enough time to set up well. You know, that's probably not very practical.
Yeah, unfortunately it's not. We rarely have that. We can get traffic away for, you know, a short period of time, but, you know, trying to get traffic off an interstate bridge widening for a week is not practical. So it definitely smoothing that transition is probably one of the most effective ways to do that.
Yeah. All right, so moving on, we'll talk a little bit about diaphragms, but we are running well ahead on time here. I think we got about 15 minutes to wrap it up.
Okay.
Yeah.
So as far as our diaphragms, with our steel girders in the closure pours, we're going to always require diaphragms. But like I told you before, we want the two to act independently of each other, the left and right stages. So we're going to typically have a slotted diaphragm with slotted holes such that they can be connected but not tightened, and as the stage 2 deflects, that diaphragm is not restricting that deflection, so the anchor or the bolts will be able to slide in that slot. For pre-stressed concrete girders, we do allow under certain considerations, eliminating diaphragms in the closure pour bay. If you stay within the guided widths that we had several slides back on the closure or the closure bay widths for concrete girders, we do allow those intermediate diaphragms to be not use those, which can save some cost and some effort on the contractor. So that's an option to think of. But if you start exceeding those recommended widths, or if we have steel girders, then the diaphragms will be required and they'll need to be slotted.
Yeah, and that's just during the to accommodate the concrete placement on stage 2. When you get to the point of actually doing the closure pour, then you want to tighten up your diaphragms.
That's correct.
Yeah.
Okay. So this is kind of looking up at the closure pour bay from underneath of a widening job, and you can see we got steel girders, steel diaphragm, and again, when we're widening, just like we would do on stage construction, when we're using steel girders, we're always going to use those diaphragms in the closure pour bay with slotted holes for the bolts. For the pre-stressed girders, we're going to use them. If we have 1 or 2 girders on our widening, we're going to use them in the closure pour bay. If you get over 2, if you have 3 or more girders, then it can potentially be eliminated in that closure pour bay, because the overall stiffness of that span would be increased. But again, leaving them loose during the pour, and then after that's poured and they're both equal on their deflections, and you do the closure pour, then that's when we tighten everything up and connect it. So we've kind of talked about traffic. Obviously, when we're widening a structure, we have to protect traffic and the workers. So we're going to use some portable temporary barrier wall. And our policy, NCDOT policy, is that anything 6 feet or more from the edge does not have to be anchored. But if it's less than 6 feet, it will have to be anchored to the deck because of the deflections of the barrier. So that's policy. But we also have to consider where that barrier wall is placed in relation to the cut line for our widening, because we have to have room to actually saw cut behind that barrier wall. So looking at least 2.5 feet, if we can get more, would be preferred. And obviously this is going to have to be something that's coordinated closely with the traffic control designers, whoever's coming up with the phasing and lane shifts, to decide where where that barrier wall can be placed. But that's one consideration we need to make as structure designers and construction to make sure we have enough room for that saw cut. So one of our most difficult maintenance items on a bridge is expansion joints, because when they leak, water gets down to our bearings and our girders, and it's just a maintenance nightmare. So we want to make sure our bridges are watertight. So we have different types of joint seals on our bridges. We use a lot of foam joint seals on certain types of structures, and they're fairly easy to phase. It's all you have to do is heat weld the two together, and it can be spliced. And so if you have stages, you can just keep adding on and welding to it. That's not a problem. One of our more popular joints is the expansion joint seal, which you can see in the picture, and it's got an embedded angle in the concrete, and then it's got a neoprene gland, and then it's got a steel hold down plate that's bolted down. And we do not allow field welding of the neoprene gland. The final gland has to be continuous from one side to the other. So that can create difficulty when you're building a bridge in stages. And so we used to not consider this until we started trying to build them with stage construction and found out that it does create these problems. And so we have been trying to emphasize the placement of the hold down plates, because they come in shorter pieces to make them more easily installed, because they can get heavy trying to place them in and bolt them. So and this is something that we're, again, just getting into, but having to coordinate with the traffic control folks, those hold down plate joints need to be located to where you can install them based on the temporary pattern, as well as considerations of where the final traffic pattern is going to be. Because if a hold down plate extends into two travel lanes and you're trying to divert traffic around it, then you're in essence affecting both those travel lanes, and you may not have room to put that traffic. So having them at a lane line to where you're only affecting one lane of traffic or two lanes of traffic is an important consideration. So again, if you are a designer that works with these expansion joint seals on a phase job, that's definitely something to coordinate on early. And then we're looking at possibly coming in and placing a new seal all the way across at the end with a temporary seal or no seal at all during the life of the project.
Okay, so we're going to switch to substructure. What we're looking at here is the end of a interior bent cap that is going to be stage constructed, where there's going to be continuity. One cap to go all the way across, out beyond the right of this particular diagram. There'll be, new cap and new column that are connected to it. We're showing a mechanical butt splice here. Typically for interior bent caps, you're looking at number 11 bars on the top and the bottom. That's very conventional to use bars of that particular size and diameter. So they have a pretty decent projection if you were to use a lap splice. And oftentimes that's not something that you've really got room to accommodate. So you deal with that by using mechanical splices and building in a shear key for boots there when you're using a cap with this sort of continuity. You can sometimes have a condition here's a photograph of that showing just kind of what that looks like. Sometimes you have a condition where you don't have continuity. In an interior bent, maybe just two independent structures side by side, and in an end bent, you can have effectively no continuity if you happen to have no load being applied in between the adjacent piles. In which case, it's not really necessary to continue your flexural steel across the span between the pile that's already in the ground and the one that's part of the next phase. Here's Aaron's going to take this one.
Yeah, sure. So this particular subject, as far as where we locate our new bents and piles compared to where the existing is. So this could apply even if you're not doing stage construction. we want to consider what our existing foundations are going to be. So in this case, you can see the abutment and then the spread footing at the bottom. They're locating the new steel piles such that they would, if there were no other considerations, you could potentially have conflict with that existing spread footing. So in stage construction, you know, we might be dealing with that more because we might have to maintain part of the existing structure while we build a new one. So in all cases, we need to consider where that is. It would make more sense to try to, you know, go maybe 5 or 6 more feet so that we're not having to deal with that conflict. In this particular case, they knew where at least the as-built plans from the existing bridge showed those footings, and on this next slide, they modified the spacing of the H piles to avoid those. But again, it's still a risk when doing something like this, so we need to try to consider where that foundation is, try to get a little further away if we can, and also don't assume that we can, you know, pull the existing piles. Sometimes they can't be pulled if that's what's in conflict. If a footing is, you know, not buried very deep, it could potentially be excavated and removed, but in that last picture, you know, you're not going to dig down that deep to remove that spread footing. So those are the types of things that need to be considered when you're dealing with existing structures.
Yeah, and just deal with it early, you know, go ahead and be coordinating on the front end with all of the involved disciplines so that you lay out the bridge in a way that's beneficial for everybody.
Another consideration for stage construction, you can see the highlighted yellow. That pile is actually not needed in stage 1. It's only needed for stage 2. But sometimes whenever you build stage 1, you start building the overhang on the superstructure, it's going to get in the way of your pile driving. You might not be able to fit your pile hammer in there to drive that pile. So that's something that as a designer you need to look out for. And if it can be driven in stage 1, even though it's not needed, to basically dot right on there that should be driven with stage 1. So anytime we can do that, we need to try to do it.
Sometimes you'll have a case where, you know, you're using an existing bridge, continuing to use an existing bridge while you've got a new structure going in, but you have to take a portion of the existing bridge away in order to fit in the new structure that you're going to be bringing in as part of a stage construction, or even just a new construction without staging. Sometimes that applies too. And then from the design engineer's perspective, we recognize when we're going to have a need for some kind of supplemental temporary works, and we'll indicate that in the plans. But unless you're on a design build project, it's typically you're just indicating you're going to have this need, and then the contractor's engineer will deal with it. And so in this particular instance, this is the before on the planning level. There's a prop, and that's what it ended up looking like.
Yeah, so the contractor will work with an engineer to design some type of temporary works, and this is what this particular contractor did. So it didn't look exactly like it was sketched on the previous drawing, but it was engineered and approved to support that cantilevered cap.
Staged approach fill.
This is the last of the topics we're going to cover. So we have to not only be able to build the superstructure and substructure, we've got to shore up and make sure, because we're going to have to excavate beside the existing structure in order to build the first stage. So in this particular case, and I would say 90-something% of the times, you're going to have at least 2 runs of shoring, and you can see it's kind of detailed there. So what you're doing is you're putting some kind of shoring. It might be sheet piles, it might be a soil nail wall, to support the existing bridge when you cut down beside it. So once you do that, you're going to build your first stage, and as you build that, you got to build it back up. So you have to have a second line of shoring to support your stage 1 roadway. Once traffic's switched to that, then it can that first wall can be removed, and then the next stage of the structure built. So this next picture will kind of let you visualize it a little bit better. So on the left, we've shored up because we had to excavate down beside the existing bridge to give us room. And then on the right side, we have built our new approach to our bridge with a temporary retaining wall. And then once traffic is shifted to that, everything on the left side will be removed and excavated, and then we'll build right up to that temporary retaining wall. In that last picture, you had a lot of room. This picture is probably more typical of what you'll see. You've only got a couple feet in between the two lines of shoring, but it's basically the same concept. Wall one supports the existing, then we build the permanent, and then shore up that side joint there with some type of temporary shoring. And this is looking at it from the other angle, so that will be used as temporary shoring, but will be just backfilled against and just remained in place as sacrificial when they go to build the next stage. So that kind of gives you a perspective of what it looks like.
Okay, so those are the all the topics that we covered here, and we wanted to open the floor up to see if anyone had any questions.
All right, thank you. So if you have questions, go ahead and type them in the questions box, and I will get those answered for you. While we're waiting to see if any questions come in, just a couple of PENC announcements. We have our Charlotte seminar next Tuesday, October 29th, and we have our Raleigh seminar coming up in December 9th through 11th at the McKimmon Center. Information about both of those are available on our website. I do not see any questions coming through, so we will go ahead and finish up. If you do have a question, you can send it to me and I can get it answered for you. You can send it to exec@penc.org, and you will receive your PDH form and your NCBL survey via email this afternoon, so be on the lookout for those. Aaron and Josh, thank you so much for being here. We really appreciate your time.
You're welcome. Glad to do it. You're welcome.
All right. Have a great day, everyone.